These ML concepts confuse even experienced data scientists. What is the purpose of stopping training when performance stops improving or starts degrading in machine learning?
Answer: stopping training when performance stops improving or starts degrading is a technique used to prevent overfitting in machine learning. Overfitting occurs when a model becomes too complex and starts to fit the noise in the training data rather than the underlying patterns. By stopping training when performance stops improving or starts degrading, the model is prevented from becoming too complex and overfitting, which saves computational resources and improves the model's generalization ability. This technique helps to strike a balance between the model's ability to fit the training data and its ability to generalize to new and seen data.
What are the key differences between PCA and TSNE in dimensionality reduction? Answer: PCA is a linear dimension reduction technique that seeks to maximize variance and preserves large pairwise distances, whereas TSNE preserves only small pairwise distances or local similarities. This means that PCA is better at capturing global structure, while TSNE is better at capturing local structure. However, both techniques can lead to poor visualization when dealing with nonlinear manifold structures. What is machine learning? Answer: machine learning is a part of artificial intelligence that helps computers learn and improve from data without being specifically programmed. It uses special algorithms to find patterns and connections in the data, and then uses these patterns to make better predictions or decisions. This technology is used in many areas, such as understanding human language, suggesting things we might like, and recognizing images. What are the main differences between supervised, unsupervised, and reinforcement learning, and how do they approach learning from data? Answer: supervised learning works with labeled data, where each input is paired with a corresponding output and the goal is to learn a mapping function. Unsupervised learning, on the other hand, analyzes unlabeled data to identify hidden patterns or structures. Reinforcement learning models learn to make decisions by interacting with an environment, using rewards and penalties to guide the learning process. These approaches differ in their goals, methods, and applications, with supervised learning focusing on specific tasks, unsupervised learning discovering patterns, and reinforcement learning making decisions in complex environments. What is overfitting? How can it be avoided? Answer: overfitting is a problem that occurs when a model becomes too specialized to the training data and fails to generalize well to new, unseen data. This can happen when a model has too many parameters or is too complex, causing it to memorize the training data rather than learning the underlying patterns. To avoid overfitting, several techniques can be used, including cross-validation, regularization, pruning, early stopping, and dropout. These techniques help to prevent the model from becoming too specialized to the training data and improve its ability to generalize to new data. By using these techniques, models can be trained to be more robust and accurate, even when faced with new and unseen data. Explain the bias-variance trade-off. Answer: the bias-variance trade-off is the relationship between the simplicity and complexity of a model. When a model is too simple, it can lead to underfitting, resulting in high bias error. On the other hand, when a model is too complex, it can lead to overfitting, resulting in high variance error. The goal is to find a balance between the two, as optimal performance is achieved by minimizing both bias and variance. Techniques like regularization and cross-validation can be used to achieve this balance. What is the difference between parametric and non-parametric models? Answer: parametric models assume a specific form or distribution for the underlying data, making them computationally efficient but limiting their ability to capture complex patterns. On the other hand, non-parametric models make no assumptions about data distribution, allowing them to adapt to the structure of the data, but requiring more data and computational resources. This difference in assumptions and flexibility makes parametric models suitable for simple relationships, while non-parametric models are better suited for complex datasets. What are training, validation, and test sets, and what is their purpose in machine learning? Answer: training, validation, and test sets are three separate datasets used in machine learning to train, fine-tune, and evaluate a model's performance. The training set is used to train the model by adjusting its parameters to minimize the error on this dataset. The validation set is used during training to fine-tune hyperparameters and prevent overfitting, ensuring the model generalizes well to new data. The test set is a separate dataset used after training to evaluate the model's performance on unseen data, giving an unbiased estimate of its accuracy. These datasets help machine learning models learn from data, avoid overfitting, and make accurate predictions. What is cross-validation? Why is it used? Answer: cross-validation is a method used to evaluate a model's ability to generalize to new, unseen data. It works by dividing the available data into multiple subsets, training the model on most of the subsets, and then testing its performance on the remaining subset. This process is repeated multiple times, with a different subset being used for testing each time. This helps to ensure that the model is not overfitting to the training data and provides a more accurate estimate of its performance on new data. Cross-validation is used to reduce overfitting and provide a more robust evaluation of a model's performance. Define precision, recall, and phone score. Answer: precision, recall, and phone score are three important metrics used to evaluate the performance of a machine learning model, particularly in classification tasks. Precision measures the proportion of true positives correctly predicted instances among all positive predictions made by the model. It represents the model's ability to avoid false positives. A high precision means that most of the model's predictions are accurate. Recall, on the other hand, measures the proportion of true positives among all actual positive instances. It represents the model's ability to detect all instances of a particular class. A high recall means that the model is able to detect most of the instances of the class. Phone score is the harmonic mean of precision and recall. It provides a balanced measure of both precision and recall. The phone score is calculated as the average of precision and recall, weighted by their harmonic mean. A high phone score indicates that the model has both high precision and high recall, making it a good overall performer. In summary, precision measures the accuracy of positive predictions, recall measures the completeness of detecting positive instances, and phone score provides a balanced measure of both. These metrics help developers evaluate and improve the performance of their machine learning models. What is the confusion matrix? Answer: the confusion matrix is a table that helps evaluate the performance of a classification model by comparing the predicted classes with the actual classes. It includes four main components: true positives TP, true negatives TN, false positives FB, and false negatives FN. This table is useful for calculating performance metrics such as accuracy, precision, recall, and phone score, which help us understand how well our model is performing. What are feature scaling techniques? Answer: feature scaling techniques are methods used to transform the values of features in a dataset to a common scale, usually between 0 and 1, to prevent features with large ranges from dominating the model's behavior. This is important because many machine learning algorithms are sensitive to the scale of the input features, and scaling can help to prevent features with large ranges from overwhelming the model. Common feature scaling techniques include min-max scaling, standardization, and normalization. These techniques can help to improve the performance of machine learning models by ensuring that all features are on the same scale, which can lead to more accurate predictions and better model interpretability. What is gradient descent? Answer: gradient descent is a popular optimization algorithm used to minimize the cost function in machine learning models. It works by iteratively adjusting the model's parameters in the direction of the steepest descent, which helps to reduce the cost function. The algorithm uses a learning rate, which controls the step size of each iteration, to find the optimal parameters that minimize the cost function. There are different variants of gradient descent, including batch gradient descent, stochastic gradient descent, and mini-batch gradient descent, each with its own advantages and disadvantages. Overall, gradient descent is a powerful tool for training machine learning models and is widely used in many applications. What is the purpose of a cost function in machine learning? Answer: the purpose of a cost function is to measure the difference between the actual output and the predicted output of a model. This helps the model learn by quantifying its performance and guiding the training process to minimize the error. The cost function is used to evaluate the model's predictions and adjust its parameters to improve its accuracy. For example, in regression tasks, the mean squared error MSE is used as the cost function, while in classification tasks, the cross-entropy loss is used. The goal of the model is to minimize this cost function during training, which ultimately leads to better predictions. Explain regularization in machine learning. Answer regularization is a technique used in machine learning to prevent overfitting, which occurs when a model becomes too complex and starts to fit the noise in the training data rather than the underlying patterns. In other words, regularization helps to reduce the complexity of the model by adding a penalty term to the loss function. This penalty term is designed to discourage the model from learning certain patterns or features that are not generalizable to new, unseen data. Regularization works by adding a term to the loss function that is proportional to the magnitude of the model's weights. This term is known as the regularization term or the penalty term. The goal is to make the model's weights as small as possible, which reduces the model's capacity to learn complex patterns and prevents overfitting. There are two main types of regularization: loan and L2 regularization. Loan regularization, also known as lasso regularization, adds a term to the loss function that's proportional to the absolute value of the model's weights. This type of regularization is useful when the goal is to select a subset of features and reduce the dimensionality of the data. L2 regularization, also known as ridge regularization, adds a term to the loss function that is proportional to the square of the model's weights. This type of regularization is useful when the goal is to reduce the magnitude of the model's weights without selecting a subset of features. Regularization is an important technique in machine learning because it helps to prevent overfitting and improve the generalizability of the model. By adding a penalty term to the loss function, regularization encourages the model to learn more generalizable patterns and features that are applicable to new, unseen data. This makes the model more robust and accurate in its predictions. What is feature engineering? Answer: feature engineering is the process of creating or transforming input variables features to enhance the predictive performance of a model. It bridges the gap between raw data and machine learning algorithms. This process involves selecting, transforming, and combining existing features to create new ones that are more relevant and useful for the machine learning model. The goal of feature engineering is to improve the accuracy, efficiency, and interpretability of the model by providing it with more informative and relevant input data. How do you handle missing values in a dataset during data cleaning? Answer: missing values can be handled in several ways during data cleaning. One common approach is to replace them with a specific value, such as the mean or median of the column. This is known as imputation. Another approach is to remove the rows with missing values, which can be done using the drop function in pandas. Alternatively, you can use interpolation to fill in the missing values based on the pattern of the data. It's also important to identify the reason for the missing values and consider whether it's possible to collect more data to fill the gaps. The choice of method depends on the nature of the data and the goals of the analysis. What are some common feature transformations used in machine learning, and how do they help in improving model performance? Answer: feature transformations are techniques used to modify the scale and distribution of features in a dataset to improve the performance of machine learning models. There are three common types of feature transformations: scaling, log transformations, and polynomial features. Scaling, also known as normalization or standardization, rescales features to a common range, usually between 0 and 1, to prevent features with large ranges from dominating the model. Log transformations convert features to their logarithmic scale, which can help to reduce the effect of outliers and improve the distribution of the data. Polynomial features create new features by combining existing features with pairs of products, which can help to capture nonlinear relationships between features. These transformations can help to improve model performance by reducing the effect of noise, improving the distribution of the data, and capturing nonlinear relationships between features. What is feature selection, and how can statistical methods like mutual information and recursive feature elimination be used to identify the most relevant features in a dataset? Answer: feature selection is a process in machine learning where we aim to select the most relevant features from a dataset to improve the performance of a model. Statistical methods like mutual information and recursive feature elimination can be used to identify the most relevant features by analyzing the relationships between the features and the target variable. Mutual information measures the statistical dependence between two variables, while recursive feature elimination recursively eliminates the least important features until a specified number of features is reached. By using these methods, we can reduce the dimensionality of the dataset, reduce overfitting, and improve the accuracy of the model. How can feature creation by combining or splitting existing features improve a machine learning model's predictive power? Answer: feature creation by combining or splitting existing features can improve a machine learning model's predictive power by creating new features that capture more complex relationships between variables. For example, combining quantity sold and unit price into a new feature, total revenue, can capture the relationship between the two variables and provide more accurate predictions. This can be particularly useful when the original features are not sufficient to capture the underlying patterns in the data, or when the model is not able to learn the relationships between the variables. By creating new features that capture these relationships, feature creation can help to improve the model's accuracy and overall performance. What are the main differences between bagging and boosting, and how do they improve the performance of machine learning models? Answer: bagging and boosting are ensemble methods that combine multiple base models to improve performance. Bagging bootstrap aggregating trains multiple models independently on random subsets of data and combines predictions through averaging or majority voting, reducing variance and improving stability. Boosting, on the other hand, sequentially trains models, where each new model focuses on correcting errors of the previous ones, assigning higher weights to misclassified examples and reducing bias while maintaining low variance. The key difference is that bagging is parallel and variance-focused, while boosting is sequential and bias-focused. These approaches can be used to improve the performance of machine learning models by reducing overfitting, improving accuracy, and increasing robustness. Question: what is the curse of dimensionality? What is sparsity in the context of data, and how does it affect machine learning models? Question: what is the curse of dimensionality? What is sparsity in the context of data, and how does it affect machine learning models? Answer: sparsity refers to the phenomenon where data points become increasingly sparse, making it challenging for machine learning models to generalize and learn from the available data. This occurs when there are fewer data points available, making it difficult for the model to capture patterns and relationships between variables. As a result, the model may struggle to make accurate predictions, classify new data points, or learn from the existing data. In essence, sparsity can hinder the performance of machine learning models, making it essential to address this issue through techniques such as data augmentation, regularization, or feature engineering. What happens to the effectiveness of algorithms like KNN or clustering when distances between points lose significance? Answer: when distances between points lose significance, it reduces the effectiveness of algorithms like KNN or clustering. This is because these algorithms rely heavily on the distances between points to make predictions or group similar data points together. If the distances are not meaningful, the algorithms may not be able to accurately identify patterns or relationships in the data, leading to poor performance. In other words, the algorithms are unable to utilize the distances between points as a reliable feature, making them less effective. What can happen to a model with too many features, and how can this issue be mitigated? Answer: a model with too many features may overfit the training data, fitting the noise rather than the meaningful patterns. This can be mitigated by using dimensionality reduction methods such as principal component analysis (PCA) or distributed stochastic neighbor embedding (TSNE) or feature selection techniques like learn regularization or mutual information. These techniques help to reduce the number of features and select the most relevant ones, preventing the model from overfitting the noise. What is principal component analysis (PCA) and how does it work? Answer: principal component analysis (PCA) is a dimensionality reduction technique that helps to transform high-dimensional data into a smaller set of orthogonal components while retaining as much variance as possible. It works by finding the directions of maximum variance in the data and projecting the data onto these directions. This results in a lower-dimensional representation of the data that captures most of the information in the original data. The steps involved in PCA are: 1. Standardization. The data is standardized by subtracting the mean and dividing by the standard deviation. 2. Covariance matrix calculation. The covariance matrix is calculated from the standardized data. 3. Eigenvalue and eigenvector calculation. The eigenvalues and eigenvectors are calculated from the covariance matrix. 4. Component selection. The components with the highest eigenvalues are selected. 5. Data projection. The data is projected onto the selected components. This process helps to reduce the dimensionality of the data while retaining most of the information, making it easier to visualize and analyze the data. How can we standardize data in a dataset to ensure all features have a mean of 0 and unit variance? Answer: standardizing data involves subtracting the mean of each feature from its values and then dividing by its standard deviation. This process ensures that all features have a mean of 0, which means they are centered around 0. Additionally, dividing by the standard deviation ensures that all features have a unit variance, which means they have the same spread. This standardization helps in comparing features with different scales and units, making it easier to analyze and model the data. For example, if we have a feature with a large range of values, standardizing it will bring its values closer to the mean, making it easier to visualize and analyze. Similarly, if we have a feature with a small range of values, standardizing it will stretch its values, making it easier to compare with other features. By standardizing data, we can ensure that all features are on the same scale, making it easier to identify patterns and relationships in the data. How do I calculate the covariance matrix to understand the relationships between features in a dataset? Answer: the covariance matrix is a square matrix that shows the covariance, a measure of linear relationship between each pair of features in a dataset. To calculate it, you need to find the average of each feature, then subtract the average from each value, and finally multiply the results by the corresponding feature values. The covariance between two features is the average of the products of the deviations of each feature from its mean. The covariance matrix is a symmetric matrix, meaning it is equal to its transpose. The diagonal elements of the covariance matrix represent the variance of each feature, while the off-diagonal elements represent the covariance between pairs of features. By analyzing the covariance matrix, you can understand the relationships between features, such as which features are highly correlated or independent. This can be useful for feature selection, dimensionality reduction, and building predictive models. What are eigenvalues and eigenvectors, and how do they relate to variance explained and directions of principal components in a dataset? Answer: eigenvalues represent the amount of variance explained by each principal component, while eigenvectors represent the directions of these components. In other words, eigenvalues tell us how much of the data's variability is captured by each principal component, and eigenvectors show us the orientation of these components in the original data space. By analyzing eigenvalues and eigenvectors, we can identify the most important features or patterns in the data and use them to reduce the dimensionality of the data while retaining the most relevant information. How do you select principal components in a principal component analysis PCA when you want to retain components that capture the majority of variance? Answer: to select principal components in a PCA, you can retain components that capture the majority of variance, for example, 95%. This means that you will keep the components that explain at least 95% of the total variance in the data. This is a common practice in PCA because it helps to reduce the dimensionality of the data while retaining the most important information. By retaining components that capture the majority of variance, you can ensure that the resulting principal components are meaningful and representative of the original data. What is the purpose of projecting data onto selected components using dimensionality reduction techniques? Answer: dimensionality reduction techniques, such as principal component analysis PCA, are used to transform the original high-dimensional data onto a low-dimensional space, which is spanned by the selected components. This process helps to reduce the noise and complexity of the data, making it more manageable and easier to visualize, analyze, and process. By projecting the data onto the selected components, we can retain the most important features and relationships while discarding the irrelevant or redundant information, ultimately leading to better insights and improved performance in machine learning algorithms. What are ensemble learning methods? Answer: ensemble learning methods are a type of machine learning technique that combines the predictions of multiple base models to improve the overall performance of the system. This is done by leveraging the strengths of each individual model while minimizing their individual weaknesses. By combining the predictions, ensemble learning methods can often achieve better accuracy, robustness, and reliability than a single model could on its own. This is because the individual models can specialize in different aspects of the problem, and the ensemble can benefit from their collective strengths. Ensemble learning methods are widely used in many applications, including classification, regression, and clustering tasks. What is bagging variance reduction, and how does it work? Answer: bagging variance reduction is a technique used to reduce the variance of a model by combining the results of multiple models trained on different subsets of the data. This is done by creating multiple models, each trained on a random subset of the data, and then aggregating their predictions to produce a final output. For example, in a random forest, multiple decision trees are trained on different subsets of the data, and their predictions are combined to produce the final output. This technique is useful for reducing the variance of a model and improving its overall performance. What is boosting, and how does it reduce bias in machine learning models? Answer boosting is a machine learning technique that reduces bias in models by sequentially training models, focusing on examples misclassified by earlier models. This process helps to identify and correct mistakes made by earlier models, resulting in a more accurate and robust final model. By iteratively learning from the mistakes of previous models, boosting can effectively reduce bias and improve the overall performance of the model. This is particularly useful in situations where the training data is imbalanced or noisy, as it allows the model to focus on the most difficult examples and learn from them. Examples of boosting algorithms include data boost, XGBoost, and gradient boosting. What is stacking in machine learning, and how does it work? Answer stacking is a technique in machine learning that combines the predictions of multiple base models using a meta-model. In other words, it's a way to combine the outputs of multiple models to make a more accurate prediction. For example, you could use a decision tree and a support vector machine SVM as the base models and then use a logistic regression model to combine their outputs. This can improve the overall performance of the model by leveraging the strengths of each individual model. The meta-model takes the outputs from the base models and uses them to make a final prediction, which can be more accurate than any one of the individual models alone. How does naive Bayes work? Answer naive Bayes is a type of supervised learning algorithm that is used for classification tasks. It works by using Bayes' theorem to calculate the probability of a new instance belonging to a particular class. The algorithm assumes that the features of the data are independent of each other, which is why it's called naive. This means that it's a simple and fast algorithm, but it's not always the most accurate. The algorithm works by first calculating the prior probability of each class, which is the probability of the class before any data is observed. Then, for each feature, it calculates the likelihood of the feature given the class and the likelihood of the feature given the prior probability. Finally, it calculates the posterior probability of the class given the data, which is the probability of the class after observing the data. The class with the highest posterior probability is then chosen as the predicted class. Naive Bayes is often used for text classification, spam detection, and image classification. It's a popular algorithm because it's easy to implement and can be used with large datasets. However, it's not always the best choice because it assumes that the features are independent, which may not always be the case. What is K-means clustering? Answer K-means is an unsupervised machine learning algorithm that groups similar data points into K-clusters based on their proximity. It works by initializing K-centroids, which are the centers of the clusters, and then iteratively updating the centroids and assigning data points to the closest centroid. This process is repeated until the centroids no longer change or a stopping criterion is met. The result is a partitioning of the data into K-clusters, where each cluster is a set of data points that are closer to each other than to data points in other clusters. K-means is widely used in data analysis, data mining, and machine learning applications. How are the initial centroids for K-means clustering determined? Answer in K-means clustering, the initial centroids are determined by randomly selecting K-points from the dataset. This is done to start the clustering process. The random selection ensures that the centroids are not biased towards a particular region of the dataset, allowing the algorithm to explore different parts of the data. The random initialization also helps to avoid getting stuck in local optima, as the algorithm can start from different initial positions and converge to the optimal solution. How do we assign each point to the nearest centroid in a clustering algorithm? Answer in a clustering algorithm, we assign each point to the nearest centroid by calculating the distance between each point and each centroid. We then choose the centroid with the smallest distance as the closest one to the point. This process is repeated for all points in the dataset, resulting in each point being assigned to the nearest centroid. This is a simple and effective way to group similar points together in a dataset. How do we recalculate centroids as the mean of assigned points? Answer to recalculate centroids, we take the sum of the x-coordinates of the assigned points and divide it by the number of points. We do the same for the y-coordinates. This gives us the new centroid, which is the mean of the assigned points. For example, if we have 3 points with x-coordinates 2, 4, and 6, and y-coordinates 3, 5, and 7, the new centroid would be 2 plus 4 plus 6/3 equals 4, and 3 plus 5 plus 7/3 equals 5. The new centroid is 4, 5. This process helps to update the centroids based on the new assigned points. What is the stopping criterion for the K-means algorithm, and what are some common use cases for it? Answer: the stopping criterion for the k-means algorithm is to repeat the process of updating the centroids until a stabilized or a maximum number of iterations is reached. This means that the algorithm will continue to update the centroids until the centroids no longer change significantly, or until a predetermined maximum number of iterations is reached. This stopping criterion is used to prevent the algorithm from running indefinitely and to ensure that the centroids converge to a stable solution. Some common use cases for the k-means algorithm include market segmentation, image compression, and anomaly detection. In market segmentation, k-means can be used to group customers based on their characteristics such as demographics and purchasing behavior. In image compression, k-means can be used to reduce the dimensionality of the image data and to compress the images. In anomaly detection, k-means can be used to identify outliers in the data that do not fit the typical patterns. These are just a few examples of the many use cases for the k-means algorithm. What is the main difference between random forest and gradient boosting, and how do they handle overfitting? Answer: random forest is an ensemble of decision trees trained independently, which reduces variance and is suitable for large datasets. On the other hand, gradient boosting is a sequential process of building trees to minimize errors, which reduces bias. However, random forest is more resistant to overfitting due to its bagging approach, whereas gradient boosting is prone to overfitting if not regularized. This means that random forest is a better choice for large datasets, while gradient boosting is more suitable for competitive scenarios where it can be regularized to prevent overfitting. Explain support vector machines SVM. Answer: support vector machines SVM is a type of supervised learning algorithm used for classification and regression tasks. It works by finding the best decision boundary, called a hyperplane, that separates different classes of data with the maximum distance, or margin. The data points closest to this hyperplane are called support vectors, and they play a crucial role in determining the position of the hyperplane. SVM is particularly useful in high-dimensional spaces and is resistant to overfitting, making it a popular choice for many machine learning applications. It also uses a technique called the kernel trick to map data into high dimensions, allowing it to find linearly separable patterns in non-linearly separable data. Overall, SVM is a powerful algorithm that can be used to solve a wide range of classification and regression problems. What is logistic regression? Answer: logistic regression is a statistical method that helps us predict the probability of something belonging to one of two categories, like 0 or 1, yes or no, or healthy or sick. It uses a special function called the sigmoid function to turn the output into a probability between 0 and 1, which is then used to make a prediction. This method is commonly used in situations where we need to identify patterns or make predictions about binary outcomes, such as detecting fraud or predicting the likelihood of a disease. What happens when two or more independent variables in a regression model are highly correlated, and how does this affect the model? Answer: when two or more independent variables in a regression model are highly correlated, it leads to multicollinearity. This causes instability in the coefficient estimates, making it difficult to interpret the model's results. The model becomes sensitive to small changes in the data, and the standard errors of the coefficients increase. This can result in unreliable predictions and the loss of confidence in the model's accuracy. What is the ROC curve? Answer: the receiver operating characteristic ROC curve is a graphical representation of the classifier's performance across different classification thresholds. It shows the trade-off between true positives and false positives, helping to evaluate the model's ability to distinguish between classes. A perfect classifier would have a ROC curve that passes through the top left corner, indicating 100% sensitivity and 0% false positives. This curve is commonly used in machine learning to assess the performance of classification models and to compare the results of different models. How does early stopping work in machine learning? Answer: early stopping is a regularization technique used in iterative training algorithms like gradient descent. It works by monitoring the model's performance on a validation set and stopping the training process when the model's performance no longer improves. This helps prevent overfitting by preventing the model from training for too long and becoming overly specialized to the training data. Instead, the model is stopped when it has reached its optimal performance on the validation set, which is a more general representation of the data. This technique helps to balance the model's ability to fit the training data and its ability to generalize to new, unseen data. What is the purpose of training the model and evaluating it on the validation set after each epoch? Answer: the purpose is to monitor the model's performance and adjust its parameters to improve its accuracy. By training the model and evaluating it on the validation set after each epoch, we can track how well the model is generalizing to unseen data and make adjustments to the model's architecture, hyperparameters, or training process to optimize its performance. This process helps to prevent overfitting, where the model becomes too specialized to the training data and fails to generalize well to new data. By regularly evaluating the model's performance, we can ensure that it is learning effectively and making progress towards its goal. How do I track validation loss or accuracy? Answer: to track validation loss or accuracy, you can use a metric such as mean squared error, MSE, or mean absolute error, MAE, to measure the difference between your model's predictions and the actual values. This will help you monitor how well your model is performing on unseen data, allowing you to adjust your model's parameters or architecture as needed to improve its performance. You can also use visualization tools to plot the loss or accuracy over time, making it easier to identify trends and patterns in your model's performance.